We now come to the last example of this section, the ninth example. Let G be the set of all 2 by 2 matrices A, B, C, D, where the entries now are coming from the set JP, the set of all integers modulo P, or there is one condition also, such that or I should write and AD minus BC is not equal to 0. If you recall, JP is the set of all congruence classes modulo P, which are elements like this. And what does the element, I mean these are congruence classes. What do we mean by that? This is the set of all integers, say n. By j we mean the set of integers in this text, such that n is congruent to I modulo P, where P is some prime. Okay. So although we say that these are integers modulo P, you should keep in mind that these are not ordinary integers. They are congruence classes. Each one of them is a set of integers. So that's what JP is. Also, recall that in JP we defined an addition and a multiplication, and we called them addition modulo P and multiplication modulo P respectively. So, and their definition were quite straightforward. If we had two congruence classes in JP, then addition modulo P by definition is just this, and multiplication mod P is defined to be this. Having defined these two operations, we then saw that just like ordinary algebra with real numbers and ordinary addition and multiplication, and the laws that are satisfied in the ordinary system of real numbers, similar laws here are also true. For example, addition is commutative associative, multiplication is commutative associative. There exists an element 0 which acts as the identity. In other words, this is a field. If you are familiar with fields, this is just like the system of real numbers is a field. This is also a field. The real number system is a field with respect to ordinary addition and multiplication. This is a field with respect to addition modulo P and multiplication modulo P. Okay. So now the matrices that we are considering have entries which are coming from JP instead of the system of real numbers. But the other condition that we previously also assumed in the sixth example, that is still there. AD minus BC is not equal to 0. Now in this condition you should keep in mind that this equation is to be interpreted as an equation in JP. That is, these A, D, B, C, these are some elements from here, and this AD, the product between this A and D, that multiplication is multiplication mod P. Similarly this one, and minus of BC is the additive inverse of the congruence class BC in the system JP. Okay, so that's how we should interpret all these things in terms of the elements and operations in JP. Fine. So now that is just the set. Now on this set we are going to again define an operation which is matrix multiplication, whose structure will be just like how we multiply to real 2 by 2 matrices. For A, B, C, D and E, F, G, H in G, we define their product like this. Shall I have space AE plus BG, AF plus BH, CE plus DG, CF plus DH. So that's how we define multiplication, which you can see is exactly like how we multiply real matrices. There is no difference between that one and this one as far as the multiplication structure goes. However, the entries that will be these operations, among the entries, these operations are addition modulo P and multiplication modulo P, because these are this A, E, B, G, these things are not real numbers, they are congruence classes modulo P. We may as well mention that where the operations among the entries are addition mod P and multiplication mod P. Now naturally the question arises whether G is a group with respect to this matrix multiplication. It is, but why? So that for that we don't have to go proving all the things, closure property, associative law, all those things. We need not prove all those things. A simple observation will tell us that this also is just like the real matrices form a group under matrix multiplication. These matrices will also form a group. But why? Let us see. Okay, let me just continue from here itself. In example 2 to 6, we have 2 by 2 matrices with real entries, where the entries are real numbers. In showing that they form a group under okay, let me just put some ink first. form a group under matrix multiplication we only used the algebraic properties of the system of real numbers, which has the set of real numbers, addition of real numbers, and multiplication of real numbers. And we can mention here, technically speaking, we used the fact that this system is a field. Field within ports, because at this stage we are not supposed to know about fields. And that's because ring theory comes only after we have studied group theory, in this text at least. But since we have already gone through ring theory and we somewhat know about fields, so we can just include the word field like this. Albeit, we can put it within quotes. It means something which we will come across only after some time. Okay, so the point here is that in showing that the 2 by 2 real matrices form a group under matrix multiplication, we only used the algebraic properties of this system, which specifically those properties which say that addition is commutative, addition is associative, addition is or multiplication is distributive over addition, those things, those properties. Taking all of them together, we have the field properties. That's why if you say that the system is a field, then at once you are saying that all those properties are true. Now the point here is that, so what? That is about example 6. So what is the relationship between this one and that one? They are similar because here also we are considering 2 by 2 matrices, and here also the operation is matrix multiplication. But the operation among the entries are something else. Addition modulo P and multiplication modulo P. But this system, where say this is addition modulo P and multiplication modulo P, just to show that they are different operations than ordinary addition and multiplication, we are putting suffix P here. This system also satisfies exactly similar properties as this system. So don't you think that just like how the real matrices formed a group, these matrices will also form a group? Keep in mind that in showing that the real matrices form a group, we used only those properties and not the fact that the entries are real numbers. Yes, of course they were real numbers, but we only used the algebraic fact that addition of real numbers is associative, real numbers are closed under addition. Similar facts are true in here also, and this is also an example of a field. In short, what I am trying to say here is that the proof that 2 by 2 real matrices form a group under matrix multiplication only depends on the fact that the entries are coming from a field. Here also they are coming from a field. So here also the matrices will form a group under matrix multiplication. That is the point. So you have to only recognize that thing, and then the rest is just it's true, automatically true. But here I should mention, since we are taking references from Tau's analysis, so C section 3.1 means section, see, whenever we write section 3.1 just like that without saying anything further, that means section 3.1 in topics in algebra in this text. And this is the first section of ring theory. So there you have the definition of field and proposition five three 11 in Tau's analysis 1. Here the fact that the real numbers actually form a field has been proved in this proposition. So you can refer to this. So now we mention this, the second thing. Similar laws are also true in the system where this and this denote addition modulo P and multiplication modulo P respectively, and that we have in fact proved way back when we were dealing with section 1.3, which deals with the set of integers in this book itself, in topics in algebra. You go to that section 1.3 and its name is integers. You go towards the end of this section, there you will encounter this JP and these two operations. Okay, so denote addition mod P and multiplication mod P respectively. This is also an example of a field. See exercise 13 and exercise 17. Of section 1.3, this section. So there you will see that we have actually proved that JP is a field, although there we did not mention the word field since that comes afterwards. Also, we have defined matrix multiplication, or better I write like this instead of writing defined matrix multiplication. Also we have defined the operation in G, just like the one in example 6. So G forms a group under this operation. Okay, so just based on this observation we can conclude that G forms a group under this operation. Now here also we have 2 by 2 matrices. The elements are coming from JP, but unlike R, JP is a finite set. So there will only be finitely many matrices. So we will now mention that. Note that G is a finite group because G is contained in the set of all such matrices without any further restriction. In our actual G we have the additional restriction that AD minus BC should be non-zero. But if you do not consider that restriction and allow A, B, C, D, all of them to vary over JP independent of one another, then you get this set. G is a subset of this, and the latter set, this set is finite. Why is it finite? You see, in these matrices, each of these 4 entries can be chosen arbitrarily from JP. How many elements does JP have? JP has P elements starting from 0 to ending at P minus 1. So, and these choices are independent. So you can make how many choices? P to the power 4 choices. With P to the power 4 elements or matrices, same thing. Okay, so unlike the example 6, there the group is infinite and non-abelian. Here the group is finite but still non-abelian. To see why that is non-abelian, you can take a very simple 2 matrices. Note, have we already written note that? Okay. Also, note that what happens when we multiply these 2 matrices. The other has 0 here. Keeping the notation of the text intact, but it looks somewhat cumbersome. It's cumbersome to always keep writing a congruence class like this. To get rid of that problem, some people denote it by this I bar. That is somewhat more convenient. Anyway, so if we calculate this product, what shall we get? 0, 1 times 1 is 1, this is again 1 plus 1 we get 2. Okay, so we do get 2. Okay, anyway, this, and let us calculate the other product now. So this gives us 1 plus 1 2, 0 plus 1 1, plus 1 1. Keep in mind that in these calculations we are taking care of the fact that the entries, the way we are manipulating the entries, that is happening in JP. So for example, the first row, first column element here is 1 times 0 plus 1 times 1, where this is addition modulo P and these two are multiplication modulo P, these operations. According to their definition, I get 1 times 0 plus 1 times 1, so that gives me 1. So that's how we are calculating. So you can see that these two matrices are not equal. Why? Because the first row, first column entry in them are different. We cannot have 1 is equal to 0. Can you guess why? And this 1 and this 0 are different things, keep that in mind. They are not numbers, they are sets, congruence classes. These matrices are different because 0 is, this 0 is not equal to 1, this one. So if these two entries are different, then the matrices cannot be same for every prime P. So it does not matter what P is, what prime P actually is. We will never have this, but what is the reason? If we want to have 0 is equal to 1, what does that mean? These are congruence classes. So if these two are equal, then 0 should, every congruence class that is represented by an element contains that element. So 0 belongs to this congruence class, so that means 0 also belongs to this congruence class. So 1 should be congruent to 0 mod P, and by definition this means P has to divide 1 minus 0, which is nothing but 1. This never happens. No prime divides 1. So that's why this cannot happen. They are never equal, and as such we get two different matrices. So these two matrices do not commute, so the group is non-abelian. Hence G is non-abelian. Now since G is finite, a natural question is to ask how many elements G has, and that question will be answered by us in one of the exercise problems. And here the section 2.2 ends, the examples of groups. After this, in the third section, we will prove some elementary facts about groups in general, and in there we will also prove that one thing which we mentioned while discussing these examples. Do you recall we defined integral powers of elements in a group, and there we mentioned laws of exponents? So that thing we will prove. Okay, so with this I end this video. It has been short, this one, because we had only one example to show.